Now next, let us look at the concept of time scaling. Okay. Now, what is the Fourier series? What is the Fourier series coefficient of a time-scaled version of x of t? Let's say x sub alpha t. So if you take this Fourier series representation, I think I have a typo here. Okay, sorry, I think I have a typo here. It should not be a negative sign. Right. So if you look at the Fourier series representation of x of t, but now just substitute alpha t into t, then you will get an expression like this. Okay. So if you observe this expression, then you will see that the Fourier series coefficients for this time-scaled version of x of t is the same as that of x of t. Okay. But you must be very careful here, because even though the Fourier series coefficients are the same, there are actually coefficients corresponding to different sets of harmonically related complex exponentials. Okay. So this is because, if x of t is periodic with respect with period capital T, then this x of alpha t would actually be periodic with a scaled period. Okay. So this is actually periodic with period t over alpha instead of capital T. Or you can say that it has a fundamental frequency of alpha omega naught. Okay. So when you look at this, you can see that it has the same Fourier series coefficients but for a different set of harmonically related complex exponentials. Okay. Right. Now, next, we can look at this property for multiplication. Okay, so suppose that you have two signals, x of t and y of t, that are both periodic with period capital T. Then first of all, you can show that the multiplication of both of these two signals are also periodic. Okay, they are also periodic with period T. Okay, and that the Fourier series coefficient of the product of the two signals is actually equal to the convolution of the Fourier series of their respective Fourier series coefficients. Okay. So multiplication of two signals in time will have a Fourier series coefficient that is equal to the convolution, the discrete time convolution of their corresponding Fourier series coefficients. Okay. Now you can also show this by directly, applying the formula for finding the coefficients, and I'm going to leave this for you to practice. Okay, so this is also done in problem 3.46 of the textbook. Okay. Now, the next property is conjugation and conjugate symmetry. Right. So this is saying that if x of t has Fourier series coefficient ak, then you can show that the complex conjugate of x of t has Fourier series coefficient that is equal to, a sub minus k with a complex conjugate. Okay. So this means that if you have a signal that is equal to a complex conjugate in the time domain, then the Fourier series coefficient will be so-called conjugate symmetric, right? It is symmetric after a conjugate, a complex conjugate. Okay. So you can also do this by direct observation of the Fourier series representation. So suppose you look at x complex conjugate of t. Right? So this is equal to the Fourier series representation of x of t complex conjugate. Okay. So when you bring this inside, you have summation k from from minus infinity to infinity ak complex conjugate e to the minus j k okay. And then by change of variable, where you set k prime equal to minus k, you get summation k prime from minus infinity to infinity a sub minus k prime complex conjugate e to the j k prime omega naught t. Okay, so this shows that the Fourier series coefficient of x of t complex conjugate is equal to a sub minus k complex conjugate. Okay. Now, if x of t is real, right, if x of t is real, which means that x of t is equal to x of t complex conjugate, okay, then this means that ak should be equal to a sub minus k complex conjugate, okay. So this is saying that if x of t is real, then its Fourier series coefficient should be conjugate symmetric. Okay. Now, furthermore, if you have x of t that is not only real, but also even, okay. Now, you know that if it is real, then ak will be equal to a sub minus k complex conjugate, okay. So you know that if it is real, then ak will be equal to a sub minus k complex conjugate. And you know that if it is even, then the Fourier series coefficient should be even as well, okay? So this is saying that if it is even, then ak should be equal to a sub minus k, okay? So this implies that ak is also real because a minus k must be equal to its complex conjugate, okay, and that it is even. So similarly, if you have x of t that is real and odd, okay, then you know that ak is equal to a sub minus k complex conjugate equal to minus a sub minus k. Okay. So if if the complex conjugate of ak is equal to minus itself, then this must mean that ak is pure imaginary. Okay, so this implies that ak is pure imaginary. Okay, and if it is odd, the Fourier series coefficient will be odd as well. Okay. So the last property I want to talk about here is Parseval's relation. Okay. So Parseval's relation is given by this equality here. Now on the left-hand side, right, what we have, on the left-hand side, what we have is 1 over t, the integral of x of t absolute squared dt over 1 period. So what you're looking at here can be viewed as the average power of the signal over 1 period. Okay. Now on the right-hand side, what you have is the summation of ak absolute squared. Now ak absolute squared, right, each one of these can be viewed as the average power in the kth harmonic component. Okay, in the kth harmonic component of the signal. Okay. Now this is because if you take the average power of the kth harmonic component, right? So if you take the average power, okay, of the kth harmonic component, which is ak e to the j k omega naught t squared dt. Okay, this is simply equal to 1 over t integral ak squared dt. And the integral over a constant, right, over one period gives you the constant times capital T, which cancels out with this, and therefore this is just ak squared. Okay. So, this relation here, right? This relation here, shape here is can be proved by directly, inserting the Fourier series representation of x of t inside this integral here. Okay, so this is also a straightforward computation, which is done in one of the problems as well. Okay, so let's leave this for problem 3.46. Okay, but it's actually very simple. You just directly substitute the Fourier series representation inside this integral on the left-hand side. Right. But this relation has has a very meaningful interpretation. Right? So it essentially tells you that the average power of the periodic signal is equal to the average power, the average power of all of its harmonic components. Okay, so this further validates the fact that this signal can be fully represented by a linear combination of these harmonic components. Okay. So again, do we have any questions up to this point?好，只有请说。
老师，我请问一下，那个下面你那 IE 那边t 分之一 k ak， 然后 exponential 那一项，为什么平方之后它就变成1啦？就是可以算一下那个是怎么变成1的吗？
你说什么东西变成1？
就是底下蓝色的右下角那个 ak exponential 那边那一项。
哦 ，OK。
为什么会变成后面的
OK， 所以因为这个 ak e to the j k omega naught t absolute square， 所以 absolute square 就是这个数字乘上它自己的 complex conjugate，right？ 所以这个会是 ak e to the j k omega naught t times ak complex conjugate e to the minus j k omega naught t. So this times this becomes a constant 1, right? So what's left is ak times ak complex conjugate.
了解，谢谢老师。
OK。好，还有没有其他的问题？
教授，
还是？
我可以问一下上面那个 AK is pure imaginary 的是什么意思吗？
所以 pure imaginary 就是说它就只有 imaginary 那一项。
可是为什么？就是它是怎么导出来的？
因为我一个数字，如果它的 complex conjugate 就是等于负的本来这个数字的话， 那这个数字一定是 pure imaginary。就是比如说你原本有一个讯号 a 加 jb 好了，那么你如果对它取 complex conjugate， 它是不是就会等于 a 减 jb？
对。
对。那如果说 a 是 non-zero 的话，那么这就不可能等于负的 a 加 jb， 对不对？所以如果 a 是 non-zero 的话，这个数字的 complex conjugate 就不可能等于负的原本这个数字。
哦，我懂了，谢谢老师。
OK。好。所以那个谢谢世贤和子佑问这些问题。那我想这些问题应该是很多其他同学想问的啊。那不知道还有没有其他问题？ Okay. So even though all these properties are quite straightforward to show, right? I hope that through more and more practice, you will be able to know all of these properties by heart, right? Because these basic properties will give you, really good insight when dealing with, signals that are much more complicated. Okay. So, in this table 3.1, we actually have a list of properties that are often encountered. Okay. So we did not go through all of these, but actually you can prove all of these following similar approaches, right? So we only touched upon this linearity, time shifting, conjugation, time reversal, time scaling, multiplication, right? So if you recall, multiplication of two time domain signals has a Fourier series coefficient that is equal to the convolution of their corresponding Fourier series coefficients. Okay. Now, if you look at the property above, you see that this property holds the other way around as well. Right. So if you take the multiplication of the Fourier series coefficients of two signals, then in the time domain, right, the corresponding time domain signal will be equal to the convolution of these two signals. Okay. So multiplication in the time domain corresponds to convolution in the Fourier series coefficients. And similarly, the other way around, multiplication in the Fourier series coefficient corresponds to convolution in the time domain signals. Okay. Now, these differentiation and integration are also very important, but we did not show them here. You could also show them directly following the straightforward computations that we just did. Okay, and we're going to use this later on when we talk about systems with, well, actually, we'll talk about them in examples coming up, but also when we talk about systems described by differential equations. Okay. Now we also looked at this conjugation, real and even, real and odd signals, and most importantly, we looked at this Parseval's relation. Okay. Now let's look at a few examples. Okay. So again, the reason for looking at these basic properties of Fourier series coefficients is because, you know, through by first obtaining the results for these, you know, basic operations, we will be able to, you know, more quickly obtain the results for more complicated scenarios. Okay. So here in example 3.6, we're looking at the case of, we're hoping to find a Fourier series representation of g of t that is equal to x of t minus 1 plus 1/2, where x of t is defined in example 3.5. Okay. So example 3.5 is the case of periodic square waves. Okay. This is the case of periodic square waves. But for the particular example that we're looking at, here we will have t1 equal to 1 and capital T, which is the period, equal to 4. Okay. So here, the x of t we're looking at is the same as example 3.5, but with t1 equal to 1, right? You can see that starting from the center extends to the left and right by 1, and with period equal to 4, right? You can see that this repeats itself after time 4. Okay. So with period 4, the fundamental frequency omega naught is 2 pi over capital T, which is pi over 2. Right. Okay. So to find the Fourier series coefficient for g of t, right, by linearity, we know that we can start out by finding the Fourier series coefficient for this term plus this term. Okay. And the Fourier series representation of this term corresponds to the time-shifted, the Fourier, okay, so this term is the time-shifted version of x of t, and we also showed the Fourier series coefficient for a time shift in the signal. Okay, so in particular, if x of t has a Fourier series representation denoted by ak, okay, then by the time shifting property, we know that x of t minus 1 has a Fourier series representation, bk, equal to ak e to the minus jk 2 pi over capital T. Okay, so this is given over here, right? So here t naught is 1, right? So we have, you know, ak e to the minus jk 2 pi over capital T, which is pi over 2 in our case, times 1. Okay. Okay. Now for the second term, minus 1 over 2, right? This is just a constant term, right? So there are no higher frequency components. Okay. So if you compute its Fourier series coefficients, you'll find that you only have a value minus 1 over 2 for k equal to 0 and 0 for all other k. Okay. So then by linearity property, we know that the Fourier series coefficient of g of t will be equal to the Fourier series coefficient of x of t minus 1 plus minus 1 over 2. Okay, so by linearity property, we know that g of t, which is equal to x of t minus 1 minus 1/2, should have Fourier series coefficient equal to bk plus ck. Okay, and if you combine this, bk plus ck is equal to, right, so this is equal to a0 minus 1/2 for k equal to 0, okay, and ak times e to the minus j k pi over 2 for k not equal to 0. Okay, so for k equal to 0, ck is minus 1 over 2, and bk for k equal to 0 is just a0 because this term becomes 1. Okay, now you can further write this. Okay, you can further substitute the values of a0 and ak from the Fourier series representation of this periodic square root, okay, that we derived before. So all right, so from this example 3.5, we showed that a0 is just 2 over t1 over t. Now in our case, t1 is 1, capital T is 4, so this is 1/2. And here ak is just again 1/2 sine 2 pi over capital T k t1. Right, t1 is 1, capital T is 4, so 2 pi over capital T is again pi over 2. Right, so substituting these parameters inside, I can get a0 and ak. Okay, so in this case, a0 is 1/2. 1/2 minus 1/2 is 0. Okay, and ak here is sine pi k over 2 over k pi e to the minus j k pi over 2. And this is for k not equal to 0. Okay, so you can see from this example that by applying first the time shifting property and then the linearity property, we can easily obtain the Fourier series coefficient for g of t with knowledge of the Fourier series coefficient of the periodic periodic square wave x of t. Okay, so using these properties, we can obtain the Fourier series coefficient of some slightly more complicated signal g of t using the Fourier series coefficient of a more simple case that we derived before, which is that of x of t. Okay. Now, in the next example, we do this again, utilizing results that we obtained for g of t.